then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
Greetings, Precalculus students. Welcome to lesson number 8. Today's lesson is about X-Intercepts. Last lesson was about Y-Intercepts. This lesson is about X-Intercepts. No need to review. I think Y-Intercepts was a fairly simple lesson. X-Intercepts are a little more difficult than Y-Intercepts, but it still should be a nice, easy lesson. So let's go ahead and get right into it. All right, X-Intercepts. So again, I want to begin with a graphical demonstration or illustration of an X-intercept. So there's the Cartesian plane, there's your x-axis, there's your y-axis. Let's introduce a graph of f of x. So there's a graph of f of x there. And this is f of x in red. And of course, the x-intercept is where it crosses the x-axis. So for this graph, this is our x-intercept here. Now, when we did y-intercepts, I was concerned about the value of x at the y-intercepts. So as you may guess, when we do x-intercepts, I'm concerned with the value of y at the x-intercept. So if you look at this x-intercept, or think about any point on the x-axis, what's the value of y have to be? And hopefully you'll say y has to be 0. So to find the x-intercept, we're just going to plug in 0 for y. And of course, solve for x. I'm not writing solve for x, but of course, after we plug in 0 for y, we're going to solve for x. Now, when we did that, when we plugged in 0 for x for the y-intercept, man, that was easy. Well, plugging in 0 for y is really not as easy, because really plugging in 0 for y is like solving the equation. For instance, if I take the following function, let's do something basic like this. So if I take this quadratic function, and again, you know, f of x is the same as y. If I plug in 0 for y, basically what I'm doing is I'm just solving the equation. And that's why x-intercepts are synonymous with solutions. So when you find a solution of an equation, it's like finding the x-intercept of the graph of that equation. They're also called zeros because it's the value of x that makes the function equal 0, or roots. So an x-intercept is really like a solution for a particular problem. And so, you know, depending on the function, to solve a function may not be the easiest thing in the world. So this definitely has a lot more to it than finding a y-intercept. So we basically have to look at solving different types of equations. So let's go ahead and find the x-intercept for this particular example. Now this is a quadratic equation. There's two main ways of solving it. There's a variety of ways, quite honestly, to solve a quadratic equation, but the two main ways are the quadratic formula and factoring. For most of us, factoring is the easiest if it can be factored, or I should say if it can be easily factored. If we can really see fairly quickly how it's factored, factoring tends to be the easiest way. And typically for a lot of us, if we can't factor, then we'll go to the quadratic formula. So this one can be factored quite nicely. So this would be x minus 4 times x plus 3. And hopefully you remember how to factor stuff like that from your previous algebra courses. And so that means that x would be 4 and -3. So that means this guy has two x-intercepts. Now, of course, as coordinates, it'll be 4, 0 and -3, 0. And that should make sense because we're plugging in 0 for y, so the y coordinate of an x-intercept should be 0, just as the x coordinate of a y-intercept should be 0. So this one has two x-intercepts. That should be understandable because you know the graph of this is a parabola, and a parabola in many cases, not in all cases, but in many cases, it's going to hit the x-axis twice. At most, it'll hit the x-axis twice. Parabola could also hit the x-axis at one point. And when solving that, we say that solution has a multiplicity of 2, something you should have heard in the previous algebra class. Parabola can also not hit the x-axis, of course. And this is a parabola that has complex roots. So complex roots do not show up on the x-axis. So we can do these things. We have something, a quadratic function, of course, is a polynomial function. And we have something called the fundamental theorem of algebra, or the corollary to the fundamental theorem of algebra, which states if the degree of the polynomial, the function has at most that many complex roots. So a second degree polynomial can have at most 2 complex roots. And when I say complex, it doesn't just have to be complex here. Real numbers are within the complex number system, so they're a part of that system. All right, so let's just look at a few more examples of finding x-intercepts of functions, of different types of functions. See if we can handle this. So these are just examples we're looking at here. So let's take another function, x, and let's say it's f of x is x minus 5 over x cubed plus 17x squared minus 99x plus 4. And I want to find the x-intercept of this guy. Now you may look at this function and say, man, this is going to be a difficult solve. I think by now you should have caught on that anytime I write a very intricate part of a function that is probably not relevant. So, I mean, there is going to be a time where we really do solve stuff like this, and a lot bigger than this. So we will at a point handle equations that look like this, and look a lot worse than this, to be perfectly honest with you. But right now you're going to handle stuff that's quite easy to maneuver with. So the question is, like, how do I solve this? Well, okay, I want to find the x-intercept, so I'm going to set y equal to 0. So y is f of x. So basically, I'm just going to set the function equal to 0 and solve. Okay, so the solution is 5. So the x-intercept is 5, 0. Now I'm going to explain, but I just wanted to write that so fast because really it's that simple. This is a rational expression. So in order for a rational expression to be equal to 0, you just have to have your numerator to be equal to 0. So this is the only thing I really need to solve. I can care less about my denominator. Well, let me say this. I can care less about my denominator except for the fact that this number cannot make my denominator equal 0, because if it also makes my denominator equal 0, then I can't solve it, because it wouldn't equal 0. It would be undefined. So, and to a certain extent, I don't care about my denominator, but this number cannot make my denominator be equal to 0. And I believe this one is not going to make this denominator equal to 0. If you don't believe me, you can plug this in and see if it equals 0 or not, but I believe it's not going to make my denominator equal 0. So therefore, when we have a rational expression, we're really going to only concentrate on the numerator being 0, because as you know, 0 over k is 0. So meaning 0 over any non-zero number is going to be 0. Now, please understand this, and this is big when you get to calculus, if you're lucky enough to make it that far in your mathematical careers. 0 over 0. Now, people have different things about 0 over 0 because you've been taught all your life a number divided by itself is 1. So some people will say 0 over 0 is 1. No, incorrect. And then other people have a thing, well, anytime you divide a number by 0 is undefined, and that rule actually works. So 0 over 0 is undefined. 0 over 0 is a very popular, what we call indeterminate form of calculus, where there's certain things that equal 0 over 0, and we find very creative ways of still solving those things, but we don't do that in pre-calculus. So just if you're lucky enough to make it to calculus, you'll begin to dissect problems that initially give you 0 over 0. All right. So anyway, that x-intercept was 5, 0. Let's look at another example of an x-intercept. So let's say this is my function. So let's say h of x is x squared plus 2 over 5x minus 3. And we're going to find, of course, the x-intercept, which basically means we're going to set this equation equal to 0 and solve it. All right. So this, of course, means we're just going to solve the numerator, of course, when we have a rational expression like this. So this is what I'm going to solve. So that's the equation you want to solve. And so understanding this equation, I'm ready to write my answer. This guy does not have an x-intercept. Now, why, you may say? Because this will never equal 0 with real numbers. If you were to try to solve this, you would subtract 2, you'll get x squared equals -2. And then x would be the square root of -2. But you can't take the even root of a negative number and get a real number back. So there's no way you can solve this with a real number. Okay, and x-intercepts are they're real numbers. So this is one of those cases where it has complex roots that wouldn't show on the x-intercept. But x-intercepts, they're real numbers, they're real solutions, they're real roots. So this guy doesn't have an x-intercept. So if you can't solve the equation, if you can't make the equation equal 0 or make the function equal 0, then you don't have an x-intercept. So again, if you cannot make the function equal 0, you do not have an x-intercept. Let's do one final example. So let's say f of x is 14 over x minus 3. We're going to find x-intercept. All right. So we need to set this equal to 0 and solve for x. What do you guys think? So pause the video if you need to and try to solve this equation for x. Okay, so you should have solved the equation. Let's see if we agree on the answer. So what I got for x, well, actually I didn't get anything for x. So this has no x-intercept. Why? For this to be 0, for this rational expression to be 0, my numerator has to be 0. The numerator is a constant. It's never going to be 0. Constants don't change, hence the term constant. So there's no way in the world this expression will ever be 0. I mean, if you just go by what we've been doing, where we're just taking our numerator and setting it equal to 0 for these rational expressions, you're left with this. And those guys are not equal. So there's no x value. There's no value you can plug in for x that will make your numerator 0. So this would never be equal to 0. So therefore, this is no x-intercept. All right, we will stop there. I hope this stuff made sense to you, and we'll see you next time.